Welcome to the session on trigonometric ratios. Review exercises. The objectives for this session are to review previous topics through exercises, namely, using trigonometry, find the missing sides or angles. And secondly, describe the effects of transformations on graphs. Pause the video and have a go at these review exercises. When you are ready to view the next set of exercises, press play. Again, pause the video and have a go at these review exercises. When you are ready to view the next set of review exercises, press play. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. Before we consider exercise 1, let's have a look at some trigonometric ratios. In a right-angled triangle, three trigonometric functions are sine theta equals opposite over hypotenuse, where the opposite is the length of the side opposite the angle theta, and the hypotenuse is the length of the side opposite the right angle. Cos theta equals adjacent over hypotenuse, where the adjacent is the length of the side next to the angle theta, and tan theta equals opposite over adjacent. So let's have a go at exercise 1a. In the diagram shown on your screen, you are required to find the length of the side x to one decimal place. The size of the angle we're considering is 25 degrees. The side x is opposite the angle, and the side, which is 3.5 centimeters long, is adjacent to the angle. So let's solve exercise 1a and find the length of the unknown side. So what do we have? We have an angle, an adjacent, and the opposite that we're required to find. Therefore, we use the formula tan. Tan theta equals opposite over adjacent. And then substituting in the values, we have tan 25 degrees equals x over 3.5. Therefore, rearranging gives us x equals 3.5 times tan 25 degrees, which implies that x is equal to 1.6. Now let's have a go at exercise 1b. Find the length of x to one decimal place. So we have an angle, and we have the side opposite to it, which is 4 centimeters, and we're required to find the hypotenuse. So if we want to solve this, we're going to use the formula sine theta equals opposite over hypotenuse. Substituting in the values gives us sine 55 degrees equals 4 over x. And rearranging gives us x equals 4 over sine 55 degrees, which implies that x is equal to 4.9. Now let's have a go at exercise 2a. We are required to find the size of theta to one decimal place. We have the side opposite to the angle theta, which is 1.5 centimeters, and we have the hypotenuse, which is 7 centimeters. So let's solve this. Since we have an angle and the opposite and the hypotenuse, we use the formula for sine. Sine theta equals opposite over hypotenuse. Substituting in the values gives us sine theta equals 1.5 over 7. and therefore theta equals sine inverse 1.5 over 7, which equals 12.4 degrees. And now for exercise 2b. Find the size of angle theta to 1 decimal place. This time we have the opposite, which is 2 centimeters long, and the adjacent, which is 3.5 centimeters. And so when we solve, we need to use the formula tan theta equals opposite over adjacent. Substituting in the values gives us tan theta is equal to opposite, which is 2, over adjacent, which is 3.5. This implies that theta equals tan inverse of 2 over 3.5. And therefore theta equals 29.7 degrees. We will now take a look at some transformations of functions before we launch into exercise 3. If we add a positive constant to x, the graph will shift left. If we take a positive constant from x, the graph will shift right. If we multiply x by -1, it reflects in the y-axis. If we add a positive constant to f of x, the graph shifts upwards. If we take a positive constant from f of x, the graph shifts downwards. And finally, if we multiply f of x by -1, it reflects in the x-axis. So let's now take a look at exercise 3. The graph of y equals f of x is shown on your screen. The graph A is a translation of the graph y equals f of x. Write down the equation of graph A. So what's happened? F of x has shifted left. Therefore, we've added a positive constant to x to make the graph shift left. The graph has in fact shifted by 2. Therefore, the function, or the new function, is y equals f of x plus 2. Now let's have a go at exercise 4. The graph of y equals f of x is shown on your screen. Sketch the graph y equals f of x minus 2. Now when we take a positive constant from x, the graph shifts right. Now our graph is therefore going to shift right by 2, since we've taken away 2 from x. And so our new graph will look something like the one you can see on your screen now in green. In exercise 5, we're going to look at stretched graphs. Graph y equals f of ax is a stretch of y equals f of x by scale factor a in the x direction. So let's take a look at exercise 5. Let f of x equal x cubed. Sketch the graphs of y equals f of 4x and y equals f of x over 4. So let's solve this. Here's y equals x cubed. And here's y equals 4x all cubed, the x coordinates being quadrupled. And here is y equals x over 4, all raised to the power 3. The x coordinates have been quartered. Now let's have a go at exercise 6. The graph of y equals f of x is as shown on your screen. Sketch the graph of y equals f of x minus 3. When we take a positive constant from f of x, the graph shifts downwards. Since we have taken away 3 from f of x, the graph has shifted down by the value 3, as shown. This brings us to the end of this session. If you have understood its contents, you should be able to use trigonometry to find missing sides or angles, and describe the effects of transformations on graphs. Thank you very much for listening.